The year is 2007. 38-year-old astrophysicist Duncan Lorimer sat hunched over his computer screen, sifting through vast amounts of archival data collected by the Parkes Observatory in Australia. Duncan is studying pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves. Duncan was engrossed in his work, navigating through a sea of information, when suddenly, the routine of searching for the familiar cadence of pulsars was interrupted by an unexpected anomaly. A brief spike in radio waves, lasting just a few milliseconds, that was around 10 to 15 times stronger than the noise around it. The waveform was very different from what we knew about pulsars. The burst produced as much energy in a few thousandths of a second as the sun does in a month. At this point, Duncan had more questions than answers. What was this intense burst of radio energy? Where had it came from? And maybe most importantly, what caused it? Duncan's discovery marked the first ever identification of what would become known as a fast radio burst. Since that discovery, thousands of FRBs have been found, but there are still many questions surrounding them and their origin. Nowadays, Duncan and his wife are professors of physics and astronomy at West Virginia University, and in 2023, Duncan and Moore were awarded the Shaw Prize, known as the Nobel of the East, for their work discovering the fast radio burst. Welcome to the Dominic Mills Podcast, and I'm your host, Dominic Mills. Today, I sit with Duncan, and we discuss his life, the discovery of the FRB, and much more involving the study of space. All of that next, but first, let's blast that intro.
Samuel cuts it back. Ohio State wins. Barry looks, fires, touchdown Buckeye. Oh my goodness! Barry Rozier, how do you do? Cousins, Ohio State, look out, ball! You don't like that? You don't like NBA basketball?
As we dive into the new year, resolutions are on the horizon. Like many people, I'm on a journey to get healthier, and sometimes we all need that extra boost. That's where Dubby comes in. Dubby Energy isn't just a supplement, it's your secret weapon to conquer your goals. Featuring Neurofactor, a game changer derived from the Arabica coffee plant, boosting brain derived neurotrophic factor by a whopping 143%. Key amino acids, B vitamins, and vitamin C work together to support your health and enhance brain function. And when it's time to hydrate, reach for Dubby Hydro. No caffeine, just electrolytes and essential vitamins. It's the perfect sidekick to your wellness journey. Exclusive to our listeners, use promo code MILLS at checkout for a fantastic 10% off. That's MILLS, MILLS. Elevate your energy, enhance your hydration. It's time to conquer 2024 with Dubby. Alrighty, I'm here with Duncan Lorimer. Duncan, thank you so much for joining me.
Thank you, Dominic. It's a pleasure to be on the show.
Yeah, I'm glad that we were able to get this going. So you're originally from the UK. Can you tell us a little bit about where you're from?
Yeah, I'm from a place called County Durham in the northeast of England. I originally grew up in a little village called Cudderston, which is on the River Tees, and was and still is a pretty small place and a good place to be a kid. Just a few hundred people in the village. When I was about 14, I moved to the sort of nearest big town, which is a place called Darlington. Its claim to fame is it's the first passenger railways originated there.
Wow,
So
that's really cool.
the steam engines back in the 1800s. Yeah.
I was looking at some pictures of Cotherstone, and it just looks like an absolutely beautiful area, just cascading greens and all over the place.
It is really nice, yeah. And it's pretty much, been that way for, hundreds of years. It just never changes every time I go back there. So I take my kids back there. We go back as a family, so it's fun.
So, what are some things people in the United States get wrong about like life in the UK in general?
Well, yeah, I wouldn't say they get too much wrong, but what I would say is that often people will just visit, like, for example, London. London is great, don't get me wrong, but there's a lot more to the UK than, just that area. And so I would encourage people that are perhaps planning a trip over there to, to look around and it's relatively easy to uh, get around by train. And so you can catch a train up into the north of England. The northeast itself is just stunningly beautiful. There's lots of really nice coastline just to the north of where I grew up and gets you into Scotland. So I would just say my one recommendation is there's a lot more to the UK than just the big cities. No, like anywhere really.
Okay, all right. Were there any hobbies or activities in your childhood that you now recognize as precursors to your later interest in science?
Um, Not really. I think I was mostly, just trying to be a kid, biking and fishing. And my grandfather was a very keen golfer, and so he tried to teach me how to play golf. I still play that to this day. It has no bearing on my yeah, scientific abilities or anything, but it's a fun way to get outside. But I'm no great golfer. I think I just like most kids though. I think I just started getting interested in
Mhm.
space from an early age, and I can remember just staring out the window, thinking about infinity, what it means to have an infinitely large universe, or going back in time and thinking about distance scales and things like that. So I've always been fascinated by the concept of space, I guess.
Okay. So, leading into that, like what was your first memory of like I'm going to like this is something I really want to pursue in terms of space in general, like astrophysics? Like, were there any pivotal moments or influences that directed you towards that?
Um, yeah, I mean, I like again, like most kids, I would watch the TV, and the space shows would come on. Over in the UK, there was one called The Sky at Night, which used to run. I don't think it runs anymore, but it ran for many years, and it just covered all aspects of astronomy. And so that was kind of cool to see all the different things that people did. It didn't necessarily make me want to be an astronomer. That didn't really come until kind of I was in college. I guess what drove me into college, though, at least wanting to learn about astronomy, was just getting the chance to actually use a telescope. Again, that's something that is really a valuable experience for people, out there. Just want to, perhaps they have young kids, they want to give them some exposure. Try to go to your local planetarium, or find some astronomy outreach, because there'll be somebody that has access to a telescope. And so for me, it was getting that access at school. We had this old telescope, and me and a few of my friends um, tried to observe a lunar eclipse. When the moon is shadowed by the Earth, and so you get this really nice red moon. And so we didn't need the telescope to really do it, but it was just cool to be able to look at the moon when it was in that state. And that got me interested in telescopes in general. And just at that time, I was really interested in math. It's still my favorite subject, and so I wanted a way to study it in a way that piqued gave me something to apply it to. And so astronomy was just, the thing to do. And so I went into college and just studied astrophysics just for curiosity's sake at that point.
Yeah, it's really interesting you mentioned planetarium specifically because that was like my first experience I could remember actually like looking at the stars and being like, wow, like it's like you said it exactly, like, trying to understand just the grand scale of the universe, just that we
Hmm.
know. I remember going with my dad. I think I was a freshman in high school. My dad and my younger brother, and just seeing the way they lit up all of the whole sky on the roof of the planetarium was just like absolutely mesmerizing. So it's
Yeah.
really cool that you had like a similar experience getting to look through a telescope like
Hmm.
that.
Absolutely. No, I think we often, as astronomers now, as speaking as a someone that does this for a living now, you often sort of take that scale for granted, and it's only when you go out and give public talks and things that you get excited again by the grand scale of things. So yeah, it's a really it's just an amazing thing for people to discover.
Yeah, and then with your work that ended up discovering the FRBs, a lot of that is like you're looking more at like numbers and readings, right? Instead of like actually like I don't know how to say it, but like looking
Mhm.
through a telescope to like see things. So
Yeah.
that's gotta like moments like that where you get like that palate cleanser almost, where it's like, oh, this is what I'm looking at. Gotta be like super rewarding.
Right. Again, once you start getting into research, it becomes very, you know, pun intended, I guess, formulaic, but very, you're often you have a very prescribed thing that you're trying to do. So in my case, it was looking for pulsars with a radio telescope, and you quickly get removed from the telescope pointing at the sky part, and you're looking at the data because that's what you have to do. But yeah, it's again, anytime you get the chance to sort of connect back to the sky and then you find something, you think, okay, wow, I'm the first person on Earth to see this particular signal. When I was starting out, it was pulsars, and I'm the first human to ever see this pulsar. So that's kind of an amazing thought. And you think about how far the signal has traveled, in pulsars, it's across the galaxy. So it's thousands of years it's taken to reach you, or hundreds of thousands of years in some cases. And, that's an amazing thing. So there's all these sort of mind blowing facts, but sometimes they get brushed under the rug a bit.
So we talked a little bit, or you mentioned pulsars. What exactly are those? And just talking about
Right.
the grand scale of how far that they have to travel. What was your early research into that like?
Right. So yeah, the reason I became a graduate student was really so I went to college, as I mentioned, and I was interested in astronomy in general, and I was interested in math, but I really didn't know that much about the different areas of astronomy, and so it was very much a learning experience. And so towards the end of my college days, I was at the University of Wales in Cardiff, and I learned about these stars called pulsars, and they represent the end states of massive stars. So our sun, it's about 4 billion years old, 5 billion years old. In another 5 billion years, it will expand greatly. Its outer layers will encompass the Earth and the other inner planets, but it won't. It'll shed its outer layers and it will become a white dwarf. Um, and that's one of the end states of stars that I was learning around about. And that's an amazing star in itself. It's about it, the core of the sun is about the mass of the Earth at that point, and it just becomes a stable star, this white dwarf. Very cool objects. But then I learned about neutron stars, which are the fate of even more massive stars. So you get a star about 5 to 8 times the mass of the sun. It will explode violently as a so-called supernova explosion. The outer layers will get blasted into space, and the core of the star is only about the size of a city. It's even smaller than the Earth. But in that core is about 1.5 times the mass of the sun. It's an incredibly dense object. It's spinning very rapidly. It has this huge magnetic field. And I was learning about these things and saying, "Wow, these are amazing." And they're actually observable. I learned that people could study them with radio telescopes, these giant radio dishes that you see pictures of, because they send out, among other things, radio waves, kind of like lighthouses. Um, you walk along the beach and you see the rotating flashlight beam from the lighthouse. For a pulsar, what you see is the rotating radiation beam as it sweeps past your line of sight,
Oh,
sends out
that's how that
these
works?
pulsing radio waves. Yeah, yeah.
That's
And so
insane.
yeah, and so people have been observing these since the late 60s. They were found, by accident. And there's a whole field of study, and that's what I got into.
Hmm.
Yeah.
So how did your professional research begin? Like, so you you start looking for these, and how do you stumble upon just, I don't know, I guess, how does radio astronomy work with that sort of thing?
Well, this was the early 90s when I got into it. So I just graduated from college. There wasn't much of an expectation to do research as an undergraduate back then. There is now. It's very common for undergraduates to do research. But back then I hadn't really done any research. I'd just taken classes. And so I show up as a graduate student. In my case, I was at the University of Manchester, and they have one of their divisions is in radio astronomy. So there's this large radio telescope. I'm looking at a picture of it on the wall here. It's called the Lovell Radio Telescope. It's a 76-meter dish in the middle of the Cheshire countryside in the northwest of England, just south of Manchester. It's an iconic structure. It's been around since the 1950s. And basically what happened, so how radio astronomy was born is after the Second World War. A lot of the folks that were involved in the radar during they were in the military doing radar activities, transferred that equipment and the knowledge to looking for radio waves from space. And so this Jodrell Bank was established shortly after the Second World War. And it was one of the, birthplaces of radio astronomy. So by the 90s, it was used to study all sorts of different types of objects. So radio astronomy, as it turns out, you can study the universe in many different ways. You can study objects in the solar system all the way out to the beginnings of the universe itself. So there's there's just all these different people working at the observatory studying these different things. And the pulsar group was one of the places that, sorry, my
It's
phone
okay.
was going. The pulsar group was one of the places that was really active in that area back then and still is. So it was just a great place to study. And so, as a student, I'd learned about what a pulsar was, basically what I just mentioned, but I really didn't know that much. And so as a student getting into research, you have to learn how to deal with the data. You learn how the data look like, and how to handle it, using various programs. Some of them exist, and then some of them you have to write yourself to manipulate the data and search for these signals.
So when you're writing a program to look for something, do you have like general ideas on stuff that you're looking for, or is it just like you're looking for patterns or anomalies in general?
Um, it's often, you often have a pretty good idea based on what's happened in the past. And so for pulsars, for example, we have a very good understanding of what the signal looks like. So just to kind of give you my quick version of what the data look like. It's basically the radio frequencies of the telescope. So imagine, FM radio, you can tune into different frequencies. The radio telescope is the same. It can receive different frequencies and it can record them all simultaneously. And so you get readouts of frequency versus time. And so you get this kind of two-dimensional graph with radio frequency on the vertical axis and time along the horizontal axis. And the pulsar signals do this really interesting thing. They all get emitted from the pulsar at once, but then as they travel across the galaxy to get to the Earth, the pulsar signals get delayed in a different way depending on what frequency they have. So the highest frequency radio waves actually travel faster and arrive at the telescope first, and then the lower frequency radio waves travel a little bit slower. And they get there later. And so what happens is that the pulse arrives at a time that depends on its frequency. And that's because, as it turns out, the Milky Way is not, a perfect vacuum. It has gas inside of it, what we call the interstellar medium. And in particular, the free electrons in that gas actually delay the radio waves in that way. So we know all of that. That's already been observed. And so we have a good understanding of what the signal will look like. And so that's our starting point. And so depending on what you're interested in studying, you might be wanting to look really in detail at those pulses. Then you might want to write a piece of code to manipulate the data to take out that delay and then really analyze the signal in more detail. So yeah, it's very much a there's no there aren't any commercially available software packages for most of these things, right? You see, a lot of what we do is based upon code that we've written specifically for that purpose.
Mm. I wanted to ask something that you a follow up to something that you said. I had no idea that there were just like pockets of gas like just hanging out in space. I thought it was like a you said the word perfect vacuum. That's so
Yeah.
how do pockets of gas, I guess, permeate
Mhm.
or
Yeah, it's a great question. So um, we, um, I mentioned that the stars, as they reach the end of their lives, they shed their outer layers. In the case of the sun, it's a quite a uh, not a particularly violent process, although it will destroy the Earth. But anyway, the outer layers of the stars would get ejected into the Milky Way, um, and supernova explosions will add to that gas. Um, but then the universe is filled with hydrogen. That's where we all started. The first stars formed from hydrogen, and that's kind of the building blocks of everything. And so, what can happen though is when a young star is formed, it's really really hot, and it sends out ultraviolet radiation that can ionize some of that hydrogen. So the hydrogen has a proton and electron, and the energy from those stars, if it hits a cloud of hydrogen, will break it up into a proton and an electron. And it's those free electrons that float around in the Milky Way that cause the pulsar signals to do what I was talking about earlier.
wow, it is
Mhm.
absolutely
Mhm.
embarrassing how little I know. Like,
Well, no,
I
don't
could
worry.
not.
It's yeah,
Wow.
uh,
That's
yeah.
so cool though. Like I
Mhm.
guess I never really thought about the process of how it worked afterwards, or I don't really know what I
Yeah.
thought how that would have happened.
Yeah, and so it's a continual cycle. So, when the stars explode, they put out more gas into the what we call the interstellar medium, and then they can also kind of cause the clouds to collapse to form new stars. And so you can get this ongoing cycle of stellar birth and death. And so stars are forming today from the collapse of gas clouds that were produced by stars from previous generations.
And that's just the pure cyclicalness, if that's even a word, I
Mhm.
doubt it is, but
Yeah,
of
yeah.
of life and just how everything works is absolutely insane.
Mhm.
Um, so what exactly is a FRB and how did you stumble upon that?
Right. So a fast radio burst, or what we call FRBs, are basically individual pulses. So I talked about individual pulses from pulsars, and so what we see from pulsars is every time its beam sweeps past our line of sight, we get a single pulse. What we end up doing for our work with pulsars is we average those pulses together. So we get like um, kind of an averaged view of the pulsar over time. And that helps us to find weak pulsars whose pulses we otherwise wouldn't be able to see because they're so faint. We sort of add a lot of them together. Fast radio bursts are a little bit different though. There is just one pulse that you see. That's it. And so it all lasts in a few milliseconds. You see the same thing. You see this sweep that I described because of the way that the pulses have traveled through space. They've been delayed in the same way, but there's only one of them. So the very first one that we found, the whole piece of data lasted less than half a second, and the sweep occurred over that half-second duration. But the pulse itself was only about 5 milliseconds wide. so 5,000ths of a second. And that was it. We only had one of them. We couldn't average any more of them. But the reason that we saw it was because it was so bright that, once you started looking for individual pulses, you couldn't not find it because it was just so incredibly bright. It was so bright that, it took us a while to really come to terms with it, because it's, often in astronomy, you're looking at very faint signals, and all the brightest things have been found, by previous generations of astronomers. But we stumbled upon this particular object because we were looking at the data in a new way. One additional thing I'll tell you about them, and then you can ask a follow-up question, perhaps, is that the delay that we saw, this half a second delay from this dispersion effect, turned out to be much, much greater than what we'd have expected from just the gas in the Milky Way. And so we not only had a very bright signal, but we had a signal that seemed to have traveled through much, much more gas. So it was much farther away. And so that very first one that we found, we estimated, it wasn't a measurement, but we estimated the distance to be a few billion light years. And so basically what an FRB is just a pulse that has traveled, across the universe, or a significant fraction of the universe, and has arrived at the Earth. And so it's, completely different to pulsars, in that sense, but we're using the same technology to find them, if you like. And so, yeah, again, what you go back to what we were talking about earlier about trying to connect it back to the science of astronomy. And you suddenly realize, wow, when this, whatever it was that emitted this pulse, that happened before the Earth was formed, and so it's traveled across the universe, and it's arrived here after billions of years of travel. The farthest one that we observed so far is actually about 8 billion light years away. Yeah. So there are cosmic beacons, is maybe a quick way of saying it.
So when we talk about it lasting only milliseconds,
Mm,
it becomes very easy to understand why it took so long for someone to be like, "Oh, what is this?" Like,
mhm,
because they had been researching. You said that they've been researching like radio waves in that sort of way for at least 20, 30 years, not
mhm.
necessarily knowing they're looking for that specific thing, but that's that's one
Yeah,
thing I'm really struggling to like. That's definition of needle in a haystack.
right, right, exactly. No, and it's the history of radio astronomy is long and rich, but basically it's gone from recording the signals on what we call pen chart recorders, and so you have this paper tape that's running along, and it just records the intensity of the telescope versus time. So it's a very kind of visceral connection that you have to the sky. You see the signals on this piece of paper, and that's how pulsars were found. But then as more pulsars were discovered, we had to average them together in the way that I was talking about earlier. And so that required, lots more computational power and techniques. But what we were doing when we found the FRB was we were kind of going back to first principles, but we were taking advantage of the fact that we were now able to collect data every millisecond in this
Mhm.
case. And we were able to put it into a computer rather than look at it on a piece of paper. We were able to see this dispersion sweep. And so that was, the data were taken in 2001, July 24, 2001 is when it actually arrived at the telescope. We didn't discover it until 2007, just because it had been analyzed to look for pulsars. But then what we were looking for were individual pulses. It took us a while to, have that thought to do it, and then to actually find it.
So when you guys were discovering these, what were the first thoughts on like what it could mean and where they could be
Mm.
where they could be coming from, I guess.
Right. Yeah. So, we already had an idea that they were very distant based on the dispersion. So we knew that they were far away and that there was way more dispersion than you could explain from the Milky Way. So we were fairly confident in that. But then that presents a problem because whatever it has to be incredibly bright if
Mhm.
you're going to be able to see it halfway across the universe. And it turns out to be, 1,000 million times brighter than any pulsar pulse that we'd seen. Um, so that was, yeah, a bit of a head scratching moment, and it still is. But basically, what we think is going on is it's coming from a compact star, and the simplest way to think about that is the duration of the pulse. Whatever the whatever the object is, it's got to be something that's small to produce something that's just a few milliseconds in duration. Like a whole galaxy can't organize itself on a time scale of a few milliseconds because it's hundreds of thousands of light years across. It has to be something like a star, um, or something even on the surface of a star that's small enough to organize itself to radiate particles out on that time scale. And so really that kind of narrows it down to what astronomers call compact objects. Things like white dwarfs that I mentioned, these stars that are the size of the Earth but the mass of the sun, neutron stars, the size of a city but the mass of the sun, and then black holes that we haven't even talked about that are, even the next thing beyond a neutron star. You keep pouring material onto a neutron star and you cause it to collapse. Those three types of objects, collectively known as compact objects, have enough energy um, and can be thought of as ingredients for FRBs. And so, right away when they were discovered, there were lots of theories for how you might produce them. And actually, at one time, there were more theories than fast radio bursts known. And now there are a few thousand FRBs that are known. But the basic idea is it's many of the perhaps, and we still don't know exactly what they are. I will say that, but one of the most popular ideas is that it has a neutron star origin, and it's coming from something, or some of the FRBs could be coming from something what we call a magnetar, an extremely magnetic neutron star that kind of has flaring events, just like the sun has solar flares. These magnetars have even more energetic events that can be seen at great distances.
So
Um,
I'm
yeah,
just thinking, like, they'd have to be on like a scale that like can't even fathom if they're traveling that far. Like, I'm just trying to think of the sheer power something would have to have that's able to do that, and
right,
how
exactly.
dense it really has to be.
Mhm. Yeah, it turns out that in a few milliseconds, it's the same amount of energy that our sun puts out in a month. Um, or in some cases, there are some are even more energetic than that. But that gives you an idea. So it's a lot of energy that's contained in that event. However, it actually turns out to be not that much compared to some other energetic objects in the universe. So supernova explosions, which I briefly mentioned, when a whole star explodes, that puts out way more energy than these FRBs. There are things called gamma ray bursts that our colleagues in the gamma ray and high energy astronomy observe. They're similar in a way to fast radio bursts in the sense that they're coming from all over the sky. But in that case, the energies are even greater because gamma rays carry much more energy than the radio waves. It turns out that these, whatever the sources are, they could actually be producing fast radio bursts without even realizing it. It's just such a small fraction of the energy that they release.
Hmm.
Um, but yeah, for us, it's still a mind-bogglingly large source of energy. But fortunately, I would say it's not something that's beyond the realm of speculation for, like, it's not crazy for me to propose that a neutron star could produce a fast radio burst, because there is enough energy there to do it.
Yeah, and it's crazy you mentioned those in black holes because it's got to be very difficult to actually like study these to a level where it's like we can definitively say that we think it's that, because they've got to be throwing off, well, supernova specifically, so much energy. And black holes, I'm under the assumption that they're very difficult to study in terms of them putting stuff out. We just know that it's like something that nothing returns like
Mhm.
from.
Right. Well, fortunately, again, just, astronomy is such a huge discipline that there are people studying all of these different things over the years. So, for example, our colleagues in X-ray astronomy have studied what are known as X-ray binaries. And so these are pairs of stars in orbit around each other, that are so energetic that they're able to release X-rays. And what is happening there is that material is, one of the stars is actually a black hole, and material, and the black hole is sucking material from the other star, its companion. And as they're orbiting around each other, as the material is spiraling into the black hole, it gets so hot that the material, that's in spiraling rubs together literally and produces heat that emits X-rays. And that's been studied, for decades now. And so we have quite a good understanding of, how much energy a black hole can produce. And then another, going off on another tangent, people that study supernovae have been doing that for years. And so they've seen supernovae in different galaxies now, and have a really good understanding of how much energy is released. And that, to the point that where they're doing quite detailed models of the collapse of the star, um, able to study really, really in quite exquisite detail. So, we're again, as in many areas of science, you're taking advantage of the results that have come before you to help you understand something new.
That's got to be a, a a really cool concept to be part of, because you may not always see the benefits of the work that you do, but looking when you're looking back on it, you're like, if this person wouldn't have done this, I would have never been able to do this.
Right. No, that's exactly it. And so, as a good example, if pulsars hadn't been discovered, we wouldn't have been able to find FRBs. And um, we only really found FRBs because we were thinking about the individual pulses from pulsars and going back and seeing if we could find examples of those in our data. And so, yeah, it's just all this. It's kind of a giant patchwork quilt of different projects, but everybody is communicating their results, and you never know when the discovery that you make, on this day, can be used 5 years later for something different. Um, it's a, yeah, it's nice to be part of that bigger community, I guess.
Yeah, and another thing that's cool is there's so much like when one thing is discovered, everybody's like trying to like they're looking over at it and they're like, I want to see like if I could recreate this, or I want to see what this means, or I want to see how my work relates to this. When you guys were first
Mhm.
discovering FRBs, what was like the general reaction amongst like your peers in terms of like how it affected their work in terms of I don't know.
Yeah, I mean, it was very interesting, and still is, to think back at the time. I actually gave uh, a colloquium, a scientific talk on the day that the paper came out on that subject. And so, it was a chance to tell people something that was brand new, because it had been like embargoed by the journal up until that point. So yeah, people just, like us, they couldn't wrap their heads around it because it was so different. You had these really luminous objects that were coming from, halfway across the universe, apparently. And the other thing that I didn't mention actually was that in our initial discovery, we kind of realized that, we're only looking at a certain part of the whole sky at any given time. And so we did an extrapolation, and we realized that very quickly that the number of bursts over the whole sky is easily several hundred per day. So there's all these objects going off, since we've been talking, like,
Mhm.
a few dozen have gone off over the sky, and we don't even realize it. And so, all of these new pieces of information were going around, and so yeah, there was a lot of interest. As you'd expect, there's a lot of skepticism, when new results come, and that's part of science. People, question, what the results are. I think it was Carl Sagan that said, "Extraordinary claims require extraordinary evidence," and so, you're beholden to the evidence that you present. You have to defend that, and it has to be, you know, stand up to scrutiny. So yeah, there was a lot of interest. But people were, like I said, they were really, they were coming up with theories, quicker than we could find fast radio bursts at one point.
And I'm assuming that while you guys are dealing with that, you also are having to deal with the kooks in the tinfoil hats that are like, oh, these are definitely from aliens, but it's like, no, we were looking at stuff from stars, not even related to that. Has that been something that was like a, I don't know, does that ever get like frustrating to deal with while you guys are looking at that? Because it's like not even in the same.
Yeah, I'm not sure really. It's something that I think we have to keep an open mind to, as we're looking. It's just really part of the scientific endeavor. You- There's been so many things that have been found in the last 20 or 30 years that it wouldn't surprise me that if someday, in our lifetimes, there is some credible signal that's coming from an extraterrestrial civilization that's actually found. It's not beyond the bounds of possibility. So with this discovery, again, that there was quite a lot of interest from that community, and you can some of those theories that were produced. You could think about an advanced civilization having enough energy to produce something like that. The problem with it, though, was that it was just coming from all over the sky, and it was just much simpler to come up with a cosmic phenomenon. And the same thing happened with pulsars decades before. The first ones that were found were so different from anything anyone had seen. You might have heard the story. They were called LGM1, LGM2, LGM3. The first three pulsars were the LGM standard for little green men, because they didn't really, they'd never seen anything like it. And so they were kind of leaving that possibility open. So for me, it's all part of the scientific process. And, I'm okay with it.
Okay. I think it's always a really interesting concept to think of, like how another civilization would try to reach us, just because you got to think of like the medium in which they would choose to try to send a message, just because we have so many different
Right.
ways that are
Mhm.
possible, and we have no idea if they would even be able to do it, or traverse through the universe
Right.
through the same
Or,
way.
or if they would even want to do it,
Yeah,
right?
true.
We're having discussions about that ourselves. Yeah.
Yeah. it's That's one of my favorite conversations I have with people. I'm like, if they've been here for 60, 70 years, they've been visiting, and we don't know that they exist, they probably want it to be that way. So, we talked earlier about future and previous generations building upon what previous generations worked on. What technological advancements do you think could hold the most promise for unlocking future mysteries with this?
Um, I think they're kind of already here, fortunately. So back in 2007, the technology for radio telescopes, at least, was such that it wasn't that easy um, to collect data in the way that I described, where you have, every millisecond you have all these readouts. You only were looking at a tiny patch of the sky, and so all of these FRBs that were coming down, most of them you missed because the field of view of the telescope was so small. That's all changed, though, in the last decade. There are a number of instruments now that are able to look at large fields on the sky. In some cases, collect data over the whole sky at once, and that is being driven by technological advances in computing, mostly high performance computing, but also artificial intelligence, to actually be able to look through all of the candidate signals that are coming as a result of that endeavor. So there are telescopes. I'll give a shout out to a couple of them that perhaps your listeners might want to check out. There's one called CHIME, CHIME, stands for the Canadian Hydrogen Intensity Mapping Experiment. And it's a collection of cylindrical dishes in British Columbia and Canada that looks at 200 square degrees of sky. The moon is about 1 square degree. So
Wow.
so a really big swath of the sky that it can see at once. And that instrument is actually dominating the FRB discovery field. It's finding three or four FRBs every day. They found thousands of them so far. And it's driving a lot of the progress in the field. There's a couple of other instruments. One is called the Deep Synoptic Array, the DSA. That's happening in the west coast of the US, and they're about to build an instrument in Nevada that will have 2,000 small dishes that will, again, have the dishes themselves have large fields of view. And then when you combine them together, you get this really excellent sensitivity. So that's coming online over the next decade. And there are other instruments too, but really what they're going to be able to do, remarkably, is for every FRB that is found, they will be able to pinpoint them on the sky to in such a way that you'll say, it's actually coming from that galaxy. Because our initial discovery, we couldn't say really where. We could say within a fraction of a degree where it was, but that's not enough to say it's definitely coming from that galaxy. But now you can do that.
And a fraction of a degree from 8 million light years away is a completely.
There's a lot of galaxies.
Yeah, that's a
in that
whole lot
space.
of.
Yeah.
So I'm assuming it's not super vast range of time that people have been able to get a more precise view of where these are coming from. Are there any galaxies or areas that it's like more are coming from here?
Yeah, it's an interesting question. They're being found in lots of different types of galaxies. And so, as with many things in science and certainly in astronomy, there's a diversity of galaxies. Some galaxies don't have very many young stars. Some galaxies have a lot of star formation, and then all things in between, really. FRBs are being found in many different types of galaxies, and they tend to be slightly more prevalent in galaxies where there is a good degree of star formation going on, which again gives some credence to this idea that they're coming. At least some of them are coming from these magnetars, because those are generally young stars. However, there is a kind of a wrench in the works, I guess, in that some of there's one particular, there's often, like, you in science, you start off with one object and then you see that it's actually, there are more like it. But right now there's one FRB that's coming from a globular cluster. And the globular cluster is basically a collection of very old stars. Our galaxy has globular clusters and they orbit the Milky Way. Those stars are typically 5 to 10 billion years old. There's not really much new star formation that goes on in a globular cluster, so it's harder to think about how you get magnetars in there. Yet there's an FRB in a globular cluster of another galaxy that has been very studied in a lot of detail.
Mm-hmm.
So people are trying to figure out ways of getting FRBs in globular clusters. One way is to have mergers of white dwarfs, which are possible in globular clusters, and those could produce one of these energetic neutron stars. But the jury is still very much open. There's a lot to be discovered. But I think thanks to all of this new technology that is really being rolled out, thanks to just a huge community of people now, there's hundreds of people doing this. A decade from now, we'll have a really clear picture, I think, of what FRBs are and how many different types of populations there are and things like that.
And that's really exciting, especially considering like there are FRBs that are repeating, right? And then because
That's
most of them
right.
are not.
Yeah, we haven't even talked about them. But yeah, there are some of them about 10% of the ones that we currently know actively repeat. The others we've only seen once.
What do we? What are some of the different characteristics about ones that are repeating?
Yeah, there are a couple of clues. Um, the when you look at the the pulses in a bit of detail, when you sort of do um, you know a systematic analysis of the pulse width, in particular, the durations of the pulses, you find that the repeating FRBs are generally broader pulses than the one-off signals.
Hmm.
And then when you look at the widths in terms of the radio frequencies, you find that the repeating FRBs are more complex. They have a more complex, what we call morphology in that frequency space than the one-off FRBs. They just tend to be a very simple sort of straight line in that space, whereas the repeating FRBs have a more complex structure. So they seem to be different, from their morphology, not only in the fact that they repeat, which again suggests that they're coming from different populations. And then there's only two sources right now where the repeating behavior seems to have some other driving factor associated with it, like a periodicity. So in one source, every 16 days, it goes through this cycle where it's active for 4 days, and then the remaining 12 days, it's off.
Hmm.
So it seems like it's being driven by some sort of periodic behavior, but that's not really very well studied in other sources yet. So we don't have a really good handle of how common that is.
Yeah, that seems like a bit of
So
an
yeah,
odd cycle to be on.
yeah, it does from, at first glance, but, if you ask an astronomer that question, they would say, oh, okay, that sort of time scale is consistent with the orbital period of a binary star system. We know of in our Milky Way, um, stars that have 60-day orbits. And so you could imagine there's like this massive star here, and let's say there's a neutron star over here, and it's going around this other star. If this massive star has a lot of material that it's spewing out of, then when the FRB source, the neutron star, if it goes through that material, it could emit a pulse as it goes through its orbit. And so that could be driving it. But it's just an idea, a theory. And we really need to study the repeater population in more detail to narrow that down. So
Well, then that's got to be something else that's really exciting about the next 5 to 10 years for sure.
right, that's right. So we'll understand more about not only where they're produced, but, how they're produced. And the other thing that I haven't even mentioned is that even if we never fully understand how what is forming them, we can already use them to study the content, the gas in the universe itself,
Hmm.
just in the same way that we study the gas in the Milky Way through pulsars. We can actually use we can see the dispersion in the FRBs to study what's known as the intergalactic medium. So that's the gas between galaxies. And so FRBs are really one of the only ways to do that. And that's what people are working on right now as well.
Is the current thought of why a lot of the gases are there from like previous star explosions and expansions?
Yeah, and there's certainly some of there's certainly some of that left over from previous formations and interactions between galaxies. But it's kind of an open question as to what drives the formation of galaxies. And so understanding the density of that gas will help us to understand how galaxies form in a bit more detail.
Okay. So tell us what it meant to become a Shaw Astronomy Laureate, something you were able to share with your wife, and tell me what that, was it something you were expecting?
Not at all, no. It was just a wonderful surprise. And yeah, we found out about 6 months ago. So yeah, my wife, who's also an astronomer, she developed a lot of the code to look for these individual pulses. And so back when it was found, we were working together, um, to use this code to search for things that eventually we found the first FRB on. And so we were getting recognized for, for that work that happened, 15, 20 years ago. And so it's a great, it was a great thrill and it was such an honor to get the award, just to recognize, work that is again built upon, as we were talking about earlier, built upon earlier accomplishments. And so we were fortunate enough to be kind of in the right place at the right time to use those things to find this new phenomenon. And it's one of those once in a lifetime things that I don't know. It's in another. If I had another go round, would I have found FRBs? I don't know. It's just it was just a really wonderful confluence of events, and so to get recognized for it was a dream come true. Yeah.
Okay. So, as a mentor and leader in the field, what advice do you offer to aspiring scientists navigating the complexities of a career in astrophysics?
Um, yeah, I think um, there's there's a lot of promise out there right now. Certainly, a lot of work to be done in astronomy in general. I would say my biggest piece of advice is for people not to get discouraged um, early on, just because it's when you're first getting started, it is overwhelming. There's so much, not only so much data now that's available to astronomers, but there are so many publications that are getting written. Like if I look at the number of publications coming out um, across all of the astronomy disciplines today, there's about 30, 40, 50 papers a day that are coming out. And so a number of those are very relevant to what I'm working on. So if you add that up every day, it quickly gets really overwhelming to try to get up to speed on all of that. So you really have to be very, very patient at first as a incoming, student, getting into this research area. So you have to be persistent, and not get discouraged if things don't work as you might um, envisage that they would. The discovery of FRBs that we talked about really was kind of the end point of many years of searching for pulsars. My wife and I had been doing that kind of work for at least 15 years at that point. So, we certainly didn't get into it to discover FRBs, but we got into it because we loved the scientific process itself. And so, but that brings so many challenges. Doing scientific research, by definition, you don't know the answers. And so again, it can get discouraging if you've come out of a classroom where, the teacher is imparting this information to you. The answers have already been figured out and you just have to learn how to do it. It's not like that. Um, it's much, you're really in charge of the whole syllabus when you're doing a research project, and you come across lots of roadblocks, things that don't work out, and you have to find ways to get around it. So yeah, it'd be very patient, and just try to learn as much as you can from this broader community that's now forming. It's very hard to do small projects in isolation now. You have to be a good team builder and be prepared to work in large groups. And it's a fascinating experience, though, and I would recommend it to anyone who's thinking about it to get into that's thinking about getting into science. But ultimately, though, just as a very long-winded answer, sorry,
You're
but
perfectly
ultimately, what you have to really find for yourself is something that you are truly interested in. And it might not be that first research project that you do. You might be initially interested in pulsars, for instance. And you find out, well, actually, no, I'm not that interested in them, but I'm interested in these things that I learned about in the process, quasars or fast radio bursts. Those interest me. And then, so be prepared to move into different areas, I guess.
Okay. I really like that answer. I think that people are gonna enjoy that at home. Um, is there anything you wanted to plug before we go?
No, I just thank you very much for having me, and I would really encourage people to like we were talking about earlier, go out and look for their local planetarium or ways to plug into some astronomy outreach that's going on, and it's just a great way to get involved in science. What we try to do is draw in people into astronomy, but often our students go out and they find other fields through that process. And so, if astronomy is the thing that's interesting you right now, go and find out as much about it as you can.
And I know I'm not sure if it's like this everywhere, but almost everywhere I've ever lived, a lot of planetariums and astronomy places do like free shows, so you don't even have to pay to see a lot of stuff.
That's right. Yeah, the show we have here, for instance, you just need to book a ticket, but it's free. So yeah, definitely check them out.
All right. Well, thank you so much for joining me today, Duncan.
Thank you, Dominic. I really appreciate it.
Oh, and why is it not end? Thank you for tuning in to this episode of the Dominic Mills Podcast. If you like the show, leave a 5-star rating or a review wherever you listen to podcasts. I'll be back in a week or so to talk NBA power rankings and preview the trade deadline. Okay, that's all for me. Hope you stay safe, stay curious.